So welcome to this second lecture in the first session, morning session of our workshop. So the next lecture is going to be delivered by my colleague Professor Partha Goswami. Partha has done his BTech in chemical engineering from Calcutta University. After that he went to IIT Kanpur for his MTech and then proceeded to do his PhD from Indian Institute of Science, Bangalore. After that he had a brief stint at CSIR Center for Mathematical Modeling, I think set up by NAL. It's a CSIR center. A CSIR Center for Mathematical Modeling in Bangalore as a scientist. So this was for about 1.5 years. After that, Partha has moved to our department. So his research interests are fluid particle suspensions, turbulent flows, CFD, and experimental fluid mechanics. And today he is going to give you introduction to this emerging area of research in chemical engineering, complex fluids. I hand it over to Partha.
Very good morning to all of you. So thanks Sachin for two reasons. One is for his nice introduction, and the second is giving me the opportunity to interact all you enthusiastic guys. Here I am going to give you a brief introduction on the present status and the opportunities in areas of complex fluids. So I will first give one brief introduction, what is complex fluids, then I will move to different types of complex fluids such as polymers, surfactants, suspensions and granular materials. Those are not the only complex fluids available in nature. The complexity is beyond, okay, but the time is limited and the patience also will be limited. So I have put the main complex fluids related to the chemical engineering disciplines. Then after putting those introduction on complex fluids, I feel this is not enough. Probably there is something which is complex flows, which consists basically of fluids. Those are simple, but when you combine themselves, that will be combine those simple fluids, it will be the nature will be basically complex. So I have put the behavior of complex flows. In general, these complex flows are also treated as complex fluids. Under this umbrella, key things which will come is the electrohydrodynamics, stability of thin liquid films, chemotaxis and microfluidics. Then obviously I do not want to lose the opportunity of advertising ourselves. So that is complex fluids at CHE IITB. Let us try to understand what is complex fluids. There is no particular definition of complex fluids. The definition is obviously a negative, which is not simple fluid, that is complex fluid. Now let us try to understand what is simple fluid. Simple fluid means, suppose you have a rectangular fluid confined in a rectangular plate. You have solved this problem in your transport phenomena classes. This is a very simple problem. Either you move one plate or you move two plates, then put the boundary conditions. You can solve simple momentum balance equation or Navier-Stokes equation to get the flow behavior. In doing so, what you consider is that stress is proportional to rate of strain. Sometimes it is called rate of deformation, but this is some spicy name, that is strain rate. So the constant which indicates the proportionality is viscosity of the fluid. That is the property of the fluid which will try to act when there is deformation, otherwise it has no role to play. Okay. Then after putting the relation in your Navier-Stokes equation, you get what should be the velocity profile. Obviously you will get linear profile provided your flow is laminar. Okay. But if your speed of this plate is very high, then you cannot solve the problem. Fluid is simple, but the phenomena is complex. So, non-linearity will play a role and the turbulence will come in the flow field. So, the profile will not be linear further. Okay. So, simple fluid is simple, phenomena is complex. Okay. Now, the fluid which follows the Newton's law of viscosity, which relates the shear stress to the deformation, is called the simple fluid. Okay. Those are purely viscous fluids. If you give them energy, there will be dissipation, ultimately there will be a balance. Okay. There is no memory effect of the fluid. Fluid cannot remember anything. Okay. The behavior is instantaneous, and after certain time it will reach to a steady state, you can get a nice velocity profile there. Okay. Now, I have introduced the simple fluids. I have taken the property which are called rheological property. Let us tell you something what is rheology is. Rheology is nothing but study of the deformation, okay, and the fluid is a substance which deforms. There is a difference between the solid and fluid. I think all of you know that for fluid we consider rate of deformation, for solid we consider only the deformation, okay, which is described by Hooke's law. Now, complex fluid does not follow Newton's law or Hooke's law. Okay. They can there might be a combination of both those, but it is not the single relation. So, the mathematical formulation which relates your shear stress with the deformation is called constitutive relation. I have written it here because constitutive relation is the only relation which makes the difference between a simple fluid and a complex fluid. So, what are the rheological properties are? Three properties are there in general we deal with: shear stress, normal stress and normal stress difference. Okay. For Newtonian fluid there is no normal stress difference like sigma xx and sigma yy, there will be no difference in case of simple fluid, Newtonian fluid, but there will be a finite difference if the fluid is non-Newtonian. Viscosity is another rheological properties. Basically, shear stress develops depending on the viscosities. We can measure the viscosities. There are different types of viscosities, either shear viscosities which I have put here as eta, and extensional viscosity also will be there, but non-Newtonian fluid there is no role. For viscoelastic fluid there are another two modulus. The physical significance is that storage modulus means it is keeping in memory. Okay. The memory effect will come. It is some sort of elastic modulus. Okay. And the loss modulus is nothing but your viscous modulus, how much energy will be dissipated, and storage modulus will take how much energy within that to react after that. Suppose there is an elastic material, after deformation if you leave, it will come to its original position as if it is remembering the things where it was, but for a Newtonian fluid it will never be able to remember that effect. Now, non-Newtonian behaviors are shear thinning behavior, shear thinning behavior, shear thickening behavior. Sometimes it is called yield stress, means the stress, minimum stress required to go over that, and others the effects are viscoelastic effects, that means with viscous forces there will be some elastic forces also. Okay. And the resultant of these viscoelastic forces are Weisenberg effect, which is a result of and some other outcome of fluid memory, and die swelling. I will explain it one by one. So, for a Newtonian fluid, if you look this curve, it is perfectly constant. Similarly, pseudoplastic and dilatant there is a change of curvature, means your viscosity is dependent on the shear rate. Bingham plastic it is linear, but you need a threshold stress, okay? Otherwise it will not deform. Now, I have classified what are the complex fluid in different everyday life. So, foods, emulsions are there like ice creams, foam, these are almost similar. Okay, gels or cheese. Now, personal care product suspensions mostly of related to surfactant, solutions and foams like shaving cream, biofluids or suspension like bloods, your gels. Okay, other solutions are there. Liquid crystals are nothing but the particular orientation of your surfactants. Okay, they will behave like liquid and crystal, that is why it is called liquid crystals. Pharmaceutical products, emulsions, the aerosols and polymers are complex fluid. Now, why do we need to understand complex fluids? Here is the reason. If not understood, they can cause immense trouble during their use. If understood, they can reveal enormous potential for application. Okay. Now, some colorful pictures. Polymers application is everywhere. Nowadays, there is restriction. So, more emphasis should be given on the research to use polymer, restriction to use polymer. Yeah. Agriculture, medicine, consumer goods, industrial goods and sports. Polymer properties. Polymer property is, as I told you, there are like memory effect. So, elastic over a short time scale, okay, and viscous over long time scale. Short time scales means it can remember the deformation for a while, okay, but if long time you give that deformation, it may not be able to remember its initial state. Okay. That is why those are called viscoelastic. Now, shear thinning behavior is observed in case of polymer. What is shear thinning? If you put shear, if you put high shear, there will be thinning, there will be decrease in viscosity. That is why it is called shear thinning. And in case similarly, it happens for extensional strain rate also, like your shear viscosity, there is extensional viscosity, that also can change. Okay. Now, what is the major parameter which major parameters which play important role in case of polymer dynamics? Those are entanglement. Polymer chains will club together and entangle with each other. Okay. That basically dictates the property which we will observe. So, entanglement increases the viscosity, reduces the shear thinning properties, like change of viscosity will reduce, but the viscosity will increase and slow down the response. Now, you can easily understand the phenomena. Suppose lots of chains are entangled together, so degrees of freedom are basically decreased. Okay. Now, if you put shear, they won't be, they are not being able to aligned. Now, suppose all of you are in queues, if I give a shear, when you are in a particular queues, you will move faster, but if you are random, then you cannot move, one will hinder the other's motion. Similar thing happens here in entanglement. Here I have used one notation, T relaxation. T relaxation means if you stretch the polymer molecule, how much time it will take to relax to its initial position, that is called relaxation time. Okay. So, that depends on again the entangling behavior. So, Deborah number basically dictates the nature of the polymer dynamics. This is nothing but the ratios of relaxation time to the experimental time scale. What is experimental time scale? The time within which you can observe the change of the property. If your experimental time scale is much more than your relaxation time, then you can observe different behavior than the other way. Here are some nice pictures. This is called Weisenberg effect. What is there? Suppose in a vessel, in a pot, you have polymer solution. Now, you are rotating. This is called a rotational quad type geometry. So, if you rotate it just by a rod, what will happen? Polymer will climb. So, it is a very well known phenomena. That is called Weisenberg effect, that happens due to the normal stress difference. For a Newtonian fluid, it will just simply rotate, or there might be some depression near the stick. But what happens? There is a normal stress which will be created in case of polymer, and since it is a free surface, it will try to climb out. Okay. Now, the climbing will depend on different interfacial phenomena and the gravity forces. Similar thing happens when there is a dye. Through the dye, suppose your polymer fluids are flowing, when it comes just out due to the normal stress, it will swell. So, this phenomena is very important to study in case of the process industry, where you use extruder very frequently, polymer processing. So, the complication in this area is memory effect. For that, sometimes we need to use a convective reference frame. Polydispersity, molecular weight of the polymer might be widely dispersed, so that your property also will change. Now, how to tackle this polydispersity in your situations? Branching will again control the outcome of the entanglement. similarly copolymers, blends and composites. So, these are the areas of interest at present. Scope of the development, polymer theory, new numerical simulation, new techniques for simulating those situations. One could be molecular simulation, really difficult, but doable probably, maybe 10 years, 20 years down the line. The next is the surfactant, we use that. Now, depending on the concentration of the, so there will be obviously hydrophilic head and hydrophobic tail, and that head might be different, non-ionic, anionic, cationic and amphoteric. Okay. So, depending on the concentration of the surfactant in your solution, there might be different phases like lamellar phases, or you can get the liquid crystalline material, or they may form a ball like structure micelles. Okay. Here are the structures. So, application is detergency, wetting, cleaning and cosmetic formulations, food and pesticides, drag reductions, but it is not that it will always happen, drag reduction. Control of the rheology, protein crystallization and microemulsions. Okay. Different structures formed by the surfactant here depending on the concentration of the surfactant. Phospholipid is one such surfactant, is a biosurfactant basically, which protects alveolar collapse in our lungs, defend against pathogens, anti-inflammatory and antioxidant, and helps in breathing, improving the lungs compliances, deformability. I have taken from a literature how rheological behavior changes. So, here is the viscosity, and depending on the different phases, your viscosity changes. That is what is important, okay? Depending on the different phases, like hexagonal, rod-like structure, disc-like structure and spherical structure. So, you see that here viscosity is low in case of the spherical structure. That might be because of the reason that one can slide over the other. Okay. So, the viscosity is very less in that case. Liquid crystals is the another outcome of the concentration dependent surfactant solutions, which are used in display as a filter and detection of the hot spot in any reacting systems. Challenges are rheological behavior with structural description. If you find there is a strong correlation between the structures, how the surfactants are orienting themselves in the fluid, and their rheological property, mainly viscosities. Okay. So, the challenge is to understand what is the structure which is giving me such rheological behavior. The structure and rheology correlation is the main challenging areas in case of surfactant as a complex fluids. Now, the case of suspension. We are the chemical engineer, we cannot do anything without thinking of suspension. Suspensions might be in a different form, like gas solid suspension, liquid solid suspensions, liquid liquid, that is called emulsion, and so on. What are the important parameters in this area? The volume fraction. Now, the particles which are in the fluid might be small, might be bigger. Depending on that, Brownian force can play important role. Okay. If the sizes of the particles in a fluid is submicron size, then Brownian force plays an important role. So, the main idea is to understand different forces and the observed behavior here. Forces might be van der Waals, forces might be electrostatic or Brownian. And to understand what are the deformation behavior is a very old Einstein relation, it is already well established, but beyond that what happens, there is a scope to understand either by numerical simulation or by experiments. Even I can tell you, if your particles are nano scale, that is nanoscale particles in a fluid, that is called nanofluids. Nanofluids are having enormous application now because of the high transport coefficient. Mass transport coefficient, heat transport coefficients, all are very high in case of nanofluids, and for nanofluids this relation is not valid. Okay. we find the viscosity will be much higher than that. So, in case of suspension, we find different behaviors, either shear thinning or shear thickening. That means, with shear viscosity can increase or can decrease. This is a phase diagram depending on the volume fraction. If you see at higher volume fraction, there might be a jammed state. Jammed state means what? It cannot flow after putting high force or stress as well. There might be shear thickening or shear thinning behavior. A crude explanation, this is a very crude explanation for that, is that suppose this is the equilibrium position, only fluid and particles are suspended in the fluid. Now, shear thinning behavior will be observed if the particles are aligned like that. So, suppose these layers are formed, now we are shearing it. This is some ball bearing actions. No? It will, one layer will slide over the other layer, then with stress your viscosity will ultimately decrease. But if they form any cluster or a particular structure which hinders the flow, then you will find that shear thickening behavior. Okay? Suppose after putting a threshold shear, those particles are aligned in such a way that they are forming some structures inside that. So, after formation of this structure, you cannot move the fluid very easily. That is why you can observe shear thickening behavior. So, I have taken that from Nature article published in 2011 or 12 around. Now, quicksand is one such suspension. It is a colloidal suspension because the sand dimensions are in the colloidal regime there, not always. Okay? You can get sand of millimeter size as well. It is called a hydrogel. So, when undisturbed behave like a solid gel, but if you disturb the equilibrium situation, then there will be a change in viscosity. So, what happens if you put your feet on quicksand, then the force required to remove your foot from the quicksand at a speed of 1 centimeter per second is about that it needs to lift a medium sized car. Suppose on a quicksand you are walking, then what happens, the structure of the sand will change because of the stress. Okay? The viscosity will decrease. Then when your foot will go inside the sand, it will reorient itself in such a way that water will come out and it will be a pure sand surrounded to your feet. So, frictional resistance will increase very high, because sand particle will have a friction between each other, and you have to put a force which is equivalent to a medium sized car. Now, there are complex fluids which are nothing but the aggregates of fat and fat crystals. Okay? The morphology of the crystal depends on the process and composition parameters like solvent, supersaturation temperature of these fat crystals, and modifying additives. So, here also you will find the correlation between the structures, which depends again on these additives and saturation temperature and all those things, and suspension rheology. So, there is a clear evidence of the structure and property relation in case of fat crystals as well. The other one is the nanostructured glass. Okay. Those are high transparent solids and glassy materials. The dynamics is detected by the glassy dynamics, that means very dense phase. Those things are in very dense phase. Application consists of encapsulation technologies to protect the material and storage of the biological materials. Challenges are listed here. So, you have to try to understand the structure and rheological property relation. To understand the structure, you can take help of the simulations, as Atik told is in his previous talk. So, you can go with a multi-scale approach to understand how the crystal will be oriented, and they will show you the observed behavior. So, you can go by comparing your simulation results with an experimental observations. In this way, you can study the arrested dynamics as well. Arrested dynamics is nothing but the dynamics when the system is very much confined and highly dense. The other thing is the granular material. Okay. This is one of the complex fluids. So, here I have listed all those. This is avalanches, rice, dals and different grains, all belongs to this granular material community. So, complexity is, where is the complexity? Sometimes you will find granular material is flowing like fluid, sometimes they are not flowing at all. Okay. So, there is a range of behaviors which can be observed depending on the surroundings and the situations. Suppose you have few knots, small knots, and the big knots are called brazil knots. So, if you take in a pot, if you just check, okay, the material density of all the knots are almost similar, the difference is only in their sizes. So, what can you think of? The bigger size particle will have bigger mass, that will go down, but it never happens. The bigger particles will come up, okay, smaller will go down. This is called brazil knot effects. You will be surprised, but there was no such explanation which could explain the situation till 2009 around. Okay. This happens basically, this can be explained based on free volume theory. The free volume surrounded to the larger particle will be much more because of their structure. Okay. So, the small knots try to go inside and make a situation such that your center of gravity exists at the bottom. Okay. That is why the bigger size knots will come up. This phenomena you have already observed in the hopper. If you fill it with granular materials, sometimes that arc formation happens and flow stops. Okay. But it will not happen every time. If your particles are very much hygroscopic, you will find arc formation. If your particles are of very small size, you may find arc formation. Okay. So, what are the parameters that controls the situation? A similar thing happens if you have a different diameter particles or different material density particles in a cylindrical chamber, and if you rotate it, the application is cement industry, rotary kiln. If you rotate it, there will be segregation. This is called band formation. In few parts, there will be large particles or higher denser particle and few smaller. This is called segregation in granular material. Now, sometimes your objective would be to mix the granular material of different shapes and size, okay, rather than segregation. In most of the time, that is the objective. Now, you have to find out the situation, or you have to design some methodology so that you can mix those. Now, how you can do that? You can do that only if you understand why it is happening. So, understanding the segregation phenomena in details is one of the challenge in case of the granular flow. So, I have listed here. If I ask you what is the constitutive relation in case of a Newtonian fluid, you will tell Newton's law of viscosity. But can you tell me what is the equation describes granular material? No, you cannot, because there is no such relation, well established relation till date. Okay. So, we are trying to investigate such a relation can explain the whole range of granular systems, which will be independent of its size, which will be independent of its surface property, or independent of the shape. Till today, there is no such relation. Okay. Already Atik has described a bit of numerical simulation. Probably this is very similar, that is why I put here. So, to find out what are the constitutive relation, sometimes it is being done that this simulation is called discrete element modeling. You take some particles, you apply the concepts of Newton's law of motion with particle-particle interactions. There are different models to arrest the interaction between the particles. You do a simulation which can take couple of days or couple of months, and try to understand what is the behavior of shear stress with velocity gradient, and try to formulate one constitutive relation. So, this is one way. Other way is to perform experiments. Okay. Now, come to complex flows. Okay. First thing which comes in our mind, we have understood hydrodynamics of Newtonian fluid, suppose. Okay. Now, if you are having emulsion type fluid, Now, if you put one electric field, what should be the behavior of, or if you have a single oil drop in water and you are putting electric field, what should be the deformational behavior of that oil drop, some sort like that. So, electrohydrodynamics is nothing but the hydrodynamical behavior in presence of an electric field. So, that can give you interface deformation, and if interface is deformed, it can change the field strength. So, what could be the equilibrium shape and size? Now, with that understanding, can we miniaturize that so that we can encapsulate drug inside that deformed bodies, or we can make a hole pore inside that lipid like structure or liposome and to put the drug inside, so that it can be used in drug delivery. Here is the pictorial presentation. Suppose here is a drop, either dielectric or conducting drops. Now, you put an electric field, you will see here the deformation is happening, okay. With different frequencies, different types of deformation will be observed. Here is the rotation. If you put a marker here, that marker will rotate, that means which indicates that the drop is the drop is rotating under electric field. If you change your field strength, sometime you will observe that this curvy structure will form on the surface, and this is called purling behavior basically. This is a curved surface and it will move like a pearl. So, this is called purling in a vesicles. With the same electric field, you can generate lots of drops on a surface in a fluid basically. So, this is called pattern formation on a planar system, or the jet, if you, suppose you have a very thin jet, if you put electric field, it will start to whip, that is called whipping of an electrified jets. Other field is chemotaxis. Chemotaxis is nothing but motion of the living cells. All of you know what is Brownian motion is, okay. But if you have a cell of the same Brownian particle size, suppose a micron size particle. Now, the question is whether that living cell will behave like one inert particle. It is not, because they can understand if there is any food inside the system. So, if you generate some gradient inside that and you put a living cell like E. coli, they behave in a different way. Their motion is called biased random motion. It is not random motion, it is biased random motion, okay. Because their motion will be still random, they will flip, they will move, but still they will sense the gradient of their concentration gradient of their food. This is called biased random walk. Another area is stability of the thin films. The application is in coating industry. Suppose you have to coat any material, so you should be concerned about the stability of the coating, either when the coating is in liquid state, whether that will wet the surface, or even if that wets, whether that wetting is really a stable wetting, otherwise during drying there will be crack formation. Similar thing can be applied in case of combustion, though the fundamental studies are same, the stability of the thin film. If there is a thin liquid sheet that can break down under certain conditions, when the hydrodynamic forces and the surface forces are equal, then from a sheet you can generate the drops. So, that understanding will help you to apply these situations in case of combustions. Another area is multiphase flow. Multiphase can appear in a different ways. Material with different state of or phases, material in same state, but with different chemical properties. Few examples are bubbly flows, droplet flows, slug flows and particle laden flows. So, when you are going to consider or predict the properties of a multiphase flow, you have to have understanding of both the phases. Suppose you have solid particles in air. Particles obviously we do not know, or we do not know how to characterize, but air is obviously a Newtonian fluid, but the combination will behave in a different way. For that you have to understand what should be the volume fraction of the solid, so that You can use some constitutive relation in case of dense solid, or in discrete or in a dilute solid, you can consider each particle individually and predict their properties. The different ways are by direct simulation, you consider both the phases and solve the equation, because for gas flow or liquid flow you know Newton's equation, and you consider each particle individually and solve their equation of motion, and jointly solve both the phases equation to get the properties. The other way is experimental investigation. There are advanced experimental techniques to understand the phenomena. Here I have put, which is something related to PIV. Suppose you are putting one laser sheet here, you are scattering that laser sheet from the seeded particle. Suppose you want to measure the velocities of fluid phase, then you have to seed the fluid phase with some small particles. If it is air, you have to give a fog, like what we used in theater. That fog, small droplets of micron size will scatter laser light. You take in the camera that image, you analyze the image and get the velocity profile of the fluid phase, that is called PIV. Similarly, micro PIV also are being used to check the flow, such flows in microscopic dimensions. Here is just a cartoon type picture to show you the complexity inside one reactor. So, next complex flows, the area is the area of importance, the recent days importance, the microfluidics. What is microfluidics? It is nothing but a miniaturized flow in micro dimension. The micro dimension is of the order of 10 to 20 micron scale. Suppose there is a high speed gas flow in that micro device. Then if I solve you to if I ask you to solve such a problem in a laminar regime, you cannot apply no slip boundary conditions, okay, in the wall, because at high speed the gas will be very diluted and your flow dimension is micro. Okay. So, that is of the equivalent of mean free path of gas molecule. That is why your no slip condition is not valid. Then you have to find out some different boundary conditions depending on the flow behavior, which will be applicable in such scenario. That is why it is complex flows. Otherwise, in case of liquid through micro channel, this condition is satisfied, no slip boundary condition is satisfied. But this miniaturized microfluidic system can be applied to synthesize polymer nanofibers or polymer nanoparticles and high throughput biological devices. The concept of microfluidics came up from the chemistry perspective to control the rate of the reaction to find out the rate equation or rate constants. Okay. And that also can be used for filterless separation technologies. Suppose you have particles with different diameter, those are passing through a 200 to 500 micron channel, they will segregate in different layers and you can separate those particles. Okay. So, that is called diameter dependent filterless separation techniques. Here few pictures of the applications, like you can generate the tissue scaffolds, and you can put electric field here also in microfluidic devices to generate nanofibers. Applications are in the area of drug delivery, particle sensor and photonic crystals. These are the generalized approach. You can take one path and go ahead to study the system. So, as I told you, electrohydrodynamics. So, a combination of electrohydrodynamics and microfluidics will give you some phenomena which can be used for such synthesis of polymer nanofibers, and that is called electrospinning as well in a single term. Okay. Now, the advertisement part. In our department, most of the areas we are pursuing, different faculties, Professor Khapkar, Mehra, Belare, Mahesh, Shuntar, Rachis, Samir, all are working in different areas of complex fluids. Professor Jubekar is working polymer and interfacial science, obviously you have heard his lecture yesterday. Myself is working on multiphase flow, Venkat is working in the areas of microfluidics and electrospinning. Jyoti is working on fat crystals, their glassy structures. Ratul is here, he is working on free surface flows and their stability. Abhijit is working on cell mechanics. Okay. After that, I want to show you one phenomena. I think I have time. Probably you would have seen that. If not, try to have a look. So, thanks Ratul who told me about this. Is a YouTube video. Okay. I think now you will agree with me that it is really complex. So, most of the colorful reference obviously is not mine. I have taken from www and few of the published article. Acknowledgement is Professor Zubekar and Jyoti for helping me in making these colorful structures of presentation, and my colleagues who have shared different informations.
Yeah, thanks Partha for a nice lecture. Before we now start the session of interaction, let me introduce my colleague Ratul Dasgupta. Ratul has joined us recently. He has done his PhD from TIFR Hyderabad.
JNCS of Bangalore actually. Yeah.
Oh, JNCS.
Yeah, JNCASR, the Jawaharlal Nehru Center for Advanced Scientific.
Okay, so TIFR is.
Yeah, this is physically separate.
And after that, he did his postdoc in Weizmann Institute of Science in Israel. So I'll request him to talk about his research. He's doing a lot of exciting research in fluid mechanics, and also I'll request Partha to talk a little more detail about his own research. He has presented what is happening on this complex fluids front, globally also what is happening locally in our department, but he'll also explain things that he has been doing. And let's begin with Ratu.
Am I audible? Yeah. Okay, so hi, maybe I'll prefer to talk standing. So I presume most of you are at a master's level, is that true? I mean, so basically I work in, I started by my PhD work, I started by doing my PhD in fluid mechanics, so I have been mostly a fluid mechanics person. And one of the areas, I mean there are many problems in fluid mechanics which are still unsolved. I mean, you will frequently hear that turbulence is an unsolved problem in fluid mechanics. There are people in physics who work in these areas. But the interesting part is that there are still many problems in laminar flows. All of you have heard about laminar flows. There are many problems in laminar flows that you could think about which occur in our daily lives, which are still not so well understood. By that I mean one doesn't really understand it from first principles. Okay, so we cannot think from very basic principles and say that we really understand this problem. So one of the areas in which I have been working is what Partha just mentioned. It's interfacial flows or multiphase flows. The terminology is slightly different in the sense that interfacial flows, I mean we are essentially looking at what is known as fluids with a free surface. Okay, yeah, so basically these are typically when you see, for example, if you encounter flow inside a pipe or something like that, okay, so you typically would like to, as an engineer, you might be interested in calculating if you inject fluid at a particular mass flow rate, what would be the pressure drop over a certain length of the pipe. Okay, now it turns out that there is another class of problems where your boundaries are not always fixed. Okay, so where, for example, you could have a channel where you are injecting fluid, but the other side of the channel is not a wall. The lower part is obviously a wall on which the fluid is flowing, but the upper part is not a wall. The fluid is free to do what it wants to do there. Okay, and this is something that we encounter all the time. For example, this bottle of water is an example of a free surface. This interface that you see shaking here is an example of an interface, and you see it is really an additional degree of freedom in the sense that if I shake this interface will do what it wants to do. Okay, and remember that this whole body of water is again constrained to be governed by the same laws of motion that we all know for a fluid. Okay, so this is an example of an interfacial flow, and this is a very rich area of fluid mechanics. It overlaps with mechanical engineering, chemical engineering, even to an extent with civil engineering, and also in physics. It's a area of interest, and the main reason is because we frequently want to know what that interface does as the flow happens. What does the interface do in time? So one of the problems that I worked on was a problem in interfacial flows, and this is what is known as a hydraulic jump. The problem is very simple to state. I'm sure all of you have seen it at some point or the other. So I'm just going to draw a simple picture, and that will tell you what is a hydraulic jump. So how many of you have know what is a hydraulic jump? Have you encountered this word before? Have you encountered anybody who has heard about hydraulic jumps before? Okay, so is there a chalk? So so this is a problem which is very simple to observe, not so easy to understand, but at least very simple to observe. So all you have to do is go near a tap where there is a basin below the tap, and just make sure that the basin has a flat surface. And let's say this is your tap, and you have some kind of something which you can rotate and switch on the water, and this jet of water falls and hits this surface which is a wall, and then starts spreading out in kind of an axisymmetric manner. Okay, so what you are going to get is a jet of water flowing out, and then you will have a thin film here. Okay, so this is a layer of fluid which is flowing. So I would encourage you to go and try this when you go back home. It's very easy to do, and if you look from the top, you will see that at a certain distance you will see that something like this happens. Now this is what I call my free surface, what I just told you, the example there. And the reason why this is interesting is because if you look at the top, look from the top, this thing will look like a circle. Okay, you can see it every day, almost every day. And this is what is known as a hydraulic jump. Okay, it's a jump because the interface is like jumping from one height to another. And it's a very interesting problem. It's also a very old problem. If you tried looking at the scientific literature, you will find that the earliest mention of this problem was almost 100 years back by a person named Rayleigh. Okay, some of you have heard about Rayleigh. Yeah, so he had kind of mentioned this problem. Now it turns out that this problem of interfacial flows, again remember this is a laminar flow problem. Okay, we can make it turbulent, of course, by pushing the mass flow rate higher and higher, and then the jump wouldn't vanish. It would start oscillating and doing things which are more complicated. But the interesting part about this problem is that you can get it under reasonably laminar conditions. Okay, so once the flow settles down, you would get a very specific radius at which this structure forms. It's a laminar steady flow, and the challenge is of course to understand why and how why should such a structure form. I mean, if I were to give you a wall and give a flow, and if I didn't tell you anything more, you would probably not expect this. Okay, you would probably just think that the fluid would just flow and fall out of the plate or whatever on which it is falling. Okay, so you wouldn't expect it to suddenly jump to a certain height and then do this. So in some sense this is kind of non-intuitive. Okay, and that's why it's interesting to understand kind of that what is this flow doing. Okay, so there are a lot of details about this problem, and I'll not try to get into all that. You can also get this phenomena in a channel. Okay, so this is not necessarily restricted. The easiest way to get this is under a tap, but you can also get this in a channel, and there also you would have a thin layer of fluid and then it suddenly jumps to another height. Okay, you can have very complicated things happening where you can have formation of waves here. If you looked at the streamline pattern, have you all encountered the word streamline in fluid mechanics? What is a streamline? Any answers? Imaginary line of what? What is any property that the line has to satisfy? Tangent something? Tangent to that line gives you the direction of the local fluid velocity. Okay. So if you plot the streamlines here, you can get a very complex flow pattern where you will have fluid here going around in circles, getting I mean, typically you would expect that if you injected some dye here, the dye would just get carried downstream. That may not be true. You may have patterns where things are trapped in a certain region and things like that. So these innocuous looking free surface flows, even in their laminar state, because of the additional degree of freedom, the free surface that it has, can throw a lot of surprises at you. Okay, they are also very challenging from a engineering viewpoint many times, because you see this interface can support waves. Okay, so for example, if I ask you the question that have you all looked at beaches, sea beaches? So you see, you have seen waves coming in from the sea, and they break, they topple over and they break, and you have a very foamy, frothy front which is created. So why do all the beaches contain sand? So where did all that sand come from? Any answers? From the? But why does a river bed not contain sand? I mean, you have seen that. Have you seen a river beach? Typically rivers don't contain a long stretch of sand, right? So why is it that the sea contains a long stretch of sand before the sea begins? Why? I mean, the river is also carrying things, right? The sea is also and depositing it to the sea. So this is where it gets interesting, because you see these interfaces support waves, and these waves can carry things. Okay, and these waves tend to come and break at the shores. Okay, so they end up depositing a lot of stuff, which this mechanism doesn't operate in rivers. Okay, so you see there are a lot of stuff which happens when you have these interfacial flows. Many times in nature they occur under turbulent conditions, but you can get very interesting problems to think about even under reasonably laminar conditions. So that's one area where I work in. The other area also of interest is what is known as an amorphous solid. Okay, this is slightly kind of different from what I have told you until now. And basically, if I give you ice, for example, if I give you a cube of ice and ask you to think about its molecular structure, what do you think is the pattern in which molecules are arranged? Any answers? Sorry? How do you think? They are orderly arranged. So there's a name for it. We call it a crystalline arrangement of pattern. Okay, in which things repeat with a certain over a certain length. Okay, so it turns out that, I mean, we have this intuitive notion of solidity. You know, where every time we think of a solid, we think of orderly arrangement pattern, orderly pattern of arrangement. Now the interesting thing is that from an engineering viewpoint, there turns out to be these broad class of materials which kind of behave like solids, which means that they have a shape, they respond to stresses in the way a normal solid would respond to. But when you probe them, when you put some kind of a device which tries to find out what is the pattern in which atoms and molecules are arranged, you find that they are all lying disordered. There is no pattern. Okay. So these are very interesting things because they are in some sense intermediate between liquids and solids. So for example, if I took a glass of water and I asked you to probe at a given instant what is the structure of atoms and molecules, you would find a very random arrangement. Okay, and this random arrangement would evolve in time, in the sense that these atoms and molecules are continuously colliding and doing a lot of very complicated things. And we have this intuitive notion of solidity where things are arranged. At most they have a mean position about which they are vibrating. Okay, but they're not really going from one place to another over long distances and colliding with each other. So these are there is this intermediate class of materials called amorphous materials, which structurally look like liquids, which means that if you look at their atomic arrangements, they look like as if it's a liquid. But when you subject them to mechanical stresses, they behave like solids. So obviously this is something which doesn't seem to behave either like a liquid completely or like a solid completely, but somewhere in between. Okay. Now this is again another area of science and engineering where there has been a lot of interest, because these objects made out of amorphous materials can possess very interesting engineering properties. Okay, so from a day-to-day perspective, they are referred to as a glass. The glass that you see on your windows is also happens to be an amorphous solid. But there are many other materials which behave like a solid, but structurally are amorphous. Okay, and one of the challenges is, of course, to understand these things from first principles, to understand why they behave the way they do, and from that understanding in turn translates into engineering and technological applications. So these are the two broad areas in which I work, and with that I think I'll just hand over.
Actually, I work on, it's audible, no? I work on turbulence. It is turbulent multiphase flows. Mainly I work on gas solid flows, but I have interest in the other regime also. What I try to understand is rather than just modeling process equipments, I try to understand what is the interaction between turbulent and particles. How turbulence change the particles properties inside any vessel, suppose maybe a reactor or maybe a pneumatic transport system. I try to understand whether the particles will be homogeneous or concentrated in few regimes, and presence of the particle, whether they change the turbulence level. Okay. That means the effect is little complicated. Turbulence will have effect on particle and particle will have effect on turbulence. So that interaction sometimes from a very microscopic level I try to understand and observe by my experimental technique. I touched upon that. It's called PIV technique. So when I am interested to visualize the flow by a laser scattering, there will be solid particle and gas flow. Gas, we inject fog, or this theater we use some smoke generator that we inject. So you will have a complicated image with particles, larger particles and gas molecules. You have to separate it and check what are the dynamics of both the phases and try to understand what are the interaction between them. This is one area. So this area consists of two things. One is theory is very difficult to do in case of turbulence. So what I do CFD type simulation, that is called direct numerical simulation. All of you are probably either doing or have done some CFD stuffs, but what I do solve Navier-Stokes equation with little rigorous manner using spectral method or Fourier transform method, and get the particle interaction by molecular dynamics type simulation, what Atik already has introduced. So that gives me the description from a simulation perspective, and I try to validate my results using experiment. That is one area. Other area, what I am trying to do it little miniaturized microfluidics, that particle separation, what I told you in my talk. In 1965, Silberberg observed one effect. Suppose you have a laminar flow in a pipe or a channel. Now, if you put a particle at any position, there are two equilibrium positions. Either particle will move along the center, or that will go to some equilibrium position in between center and wall. That position depends on the ratio of particle to channel diameter. Okay. So, there is no clear explanation for this. Okay. Roughly it has been explained, that phenomena. I do little CFD to try to understand that and apply that in a micro channel level. Suppose my particles are of micron size and channel dimension is micro, liquid flow. I am searching whether I can separate the particles depending on their diameter or deformability when those particles will flow in a channel. Can I separate those? Okay. That can be applied in a biological field also, depending on the safe size cell screening or something. Okay. There I have devised, almost it will work maybe a couple of months or 6 months, micro PIV. So, through microscope you just scatter the similar laser light and take the image in a camera and do micro PIV experiment to find out the flow structure surround to the particle and understand whether there is any lateral force which is helping the particle to migrate. So, now I think.
So, before we start session for questions, answers or any interaction, I will request my colleague Professor Jyoti Seth to say a few words about her research area.
So, yeah, hello everyone. Of course, the session is about fluids, and I'll tell you very briefly about some of the problems that I work on. Professor Ratul talked about amorphous materials, and he talked about how these materials at a microscopic scale have a liquid-like structure, but when you look at them, they appear like solids. I work on very similar materials. Another interesting point of these materials, and some of the things that I had worked with, was also that they tend to not have length scale selectivity. So, when you say talk of flow around a sphere, you know that the diameter of the sphere is important, right? It features in the Reynolds number, it will feature in other non-dimensional numbers as well. But in certain dense materials, where interactions between particles are giving rise to those amorphous structures, what has been found is the length scale doesn't seem to be important. So, if your particles are, say, nanometer sized, or they are micron sized, or they are millimeter sized, all these materials within a given set of conditions behave in exact the same fashion, right? So, I work on materials like these. They could involve, say, microgels, which are cross-linked polymer particles swollen with a solvent, and they are around nanometer sized. These materials could be foams, for example. So, foam is nothing but an air and liquid suspension, if you may call it. So, you've seen foams from soaps and other materials. They are around mm sized. You can sometimes even see the droplets, right? So, that's an example of a very large scale material. But a foam as such, if you hold it in your hand, appears like a solid, but it has nothing but air and liquid present, right? So, somehow the interfacial interaction at the air-water interface, you have a surfactant sometimes to assist it, or a clay particle, or some other such agent, but it's somehow holding the entire material together. Right? So, a material with almost all liquid, all fluid, or very small amount of solids can act like a solid in most conditions, right? So, these are some one aspect of the materials that I'm working with. Another example are surfactants, right? So, surfactants is something which you encounter day in and day out. You encounter soaps, shampoos, I don't know, creams, loads of things. But soap, for example, is again, it is nothing but a matrix. Now it's the inverse matrix, which has a lot of solid present in it, about 60 to 70% solid, but interspersed inside the solid are liquid pockets. So I don't know if you've sometimes seen a bad quality soap can often sort of just over time just break, right? I don't know if you have or haven't observed such things. But again here, what is important is how this matrix, which is solid, interacts with the interspersed material, interspersed fluid, and how over time the interaction between them sort of lead to a slow evolution of the material. Now this very slow evolution is also termed as aging. In glassy materials or in materials with the amorphous microstructures, this aging phenomena is very, very slow and sort of proceeds at a logarithmic scale, a logarithmic time scale. Now what do I mean by a logarithmic time scale? So, so let's say we take some material here and we begin to shear it in some fashion. Say I put a disc on it and I start rotating the disc on it. Right? If I stop rotating the disc, because the material inherently has some solid-like nature, it wants to sort of recoil or sort of regain all the deformation that it occurred on it. Right? Now the logarithmic time scale comes into play. Initially, the regain of deformation is pretty quick, right? But as time proceeds, the time it takes to regain an equivalent amount of deformation increases exponentially. Right? So if you're sort of observing this material over time, what you'll find is that the deformation is increasing faster, but as you go on and on, the slope of this line is going to be almost flat. But when you see it on a logarithmic scale, it's as good as linear on that scale. Right? So now where is this important? So say if you have, you know, that projector, if had it been hanging by, say, a plastic rod, and if the plastic rod were aging over time, then the question is, will the rod remain as such over time? Or maybe after a couple of years, 5 years, 10 years, or 50 years, is this rod going to move down? Right? Because it's under a constant strain. And it's a question of how much time does it take for that stress to impart a particular strain on that rod. Right? So this is sort of in brief the kind of problems I look at. And yeah. I think I'll stop here.
Probably not the kind of things that they have presented, but certainly you have something to ask. Other questions? Yeah?
I want to know the granular material.
Suppose you have some particles with larger dia and smaller dia in a vessel, some small pot, but material density is almost similar for all the particles. Now if you shake it, shaking means you are giving some energy. If you shake that, then the larger particle will come up, top, okay? That can be explained from the free volume theory, volume surrounded to the particle. Now your system, after getting some energy, it will try to be equilibrated in such a fashion that center of gravity exists at the lower level. Okay? Now if the smaller particle come at the lower level, then it will be much more packed. So overall center of gravity will be at the lower level. That's why when there will be a shaking, smaller particle will try to penetrate at the bottom in the gap of the larger particle. And obviously larger particle will come up. That is the reason. But if you try to explain it from individual particle level, you won't be able to explain it. That happens in case of packed structure. Okay? Because larger particle will obviously have larger mass. That should not go up. So it is counterintuitive phenomena. No slip condition, in general, suppose you have a channel or a pipe, there is a liquid or gas flow. What is the no slip condition? At the wall you put 0. Because why? Your wall is having very high viscosity. Okay? So for that reason, wall is not moving. Fluid is not being able to move it, though you supply the energy or pressure drop to the fluid. So that's why your wall is stationary. Now the particles, gas particles or liquid particles, which is attached to that, the wall of the channel or the pipe will try to retard that. So in a thin layer of fluid also, the molecule of fluid will be having no velocities, zero velocity. Or if your wall moves, it will have the wall velocities. Okay. That means you are putting a no-slip condition in such a way that there is a very high introduction of a thin liquid layer, suppose single molecular layer, to the wall there. But if your system is very dilute, suppose in case of a microchannel, you have a very high speed gas flow, then what happens? The gas particles are, it happens generally for gas, that's why I am telling gas. Liquid, it is not valid. Gas particles are separately, the distance between one gas molecule to the other is very high, and they travel a path between two successive collisions that is called mean free path. Okay. Now if your mean free path is of the order of your channel length scale, means suppose channel diameter or pipe diameter, so between each collision of the molecules, they will collide with the wall. So you can think of in a way that particle will come, they are colliding with the wall and they are going. There is no continuity which is valid within the small region. Okay? So it is, the collisions are very discrete. Particles are coming, colliding with the wall and going. That means the particle will have some velocities, even net velocities, even they are near the wall. That's why you cannot put zero velocities to the particles which are very big. There will be some slip. That means some net velocities will be there. It is because they are always moving and they are colliding very rarely between each, but very frequently with the wall of the channel. Okay?
So what are the flow patterns for semi-solid fluids or plasmatic fluids?
In which case?
In general case, like for liquid, we follow laminar pattern.
It will be governed by the density. How much? Like your slurry case. It will be governed by the density. In case of, actually what happens, suppose in a fluid you have suspended particles. Now in case of suspended particles, again you cannot put no slip conditions. Particles will be having a very flat profile inside any confined geometry. But in laminar regime, your fluid will be having parabolic profile. So it is basically interplay between those two, which will govern the overall profile. Okay. Semi-solid, flow of semi-solid material.
So as Professor Partha said, it essentially will depend on what regime you are in. So if you are in a very dilute regime, for example, then all the only correction that you apply to say the flow of the solvent or the continuous medium is a slight increase in viscosity. Right? So there's something known as a Newton's equation, which gives you about 5% increase in viscosity. Now if you increase, say, the number of particles further, which means the dispersed phase packing fraction has increased further, then the increase that you expect in viscosity gets, has some non-linearities associated with it. So further what will happen is, if these particles are, say, attractive or repulsive, yeah, so say if the particles are charged, then as two particles try to come closer together, they are going to have a repulsive force between them. So now that will contribute to the viscous forces that you measure as well. So just like that, there are a number of forces that you have to take into account before, say, predicting how the material will behave under an applied stress.
Just I'll add one point regarding the no-slip condition. There is a German resonance from Indian Academy of Science, and there is one article on no-slip condition. Have a look at it. Yes, that will be suggested this way.
This journal is for all of your kids. It started audience is you are still at master's level. So this journal is published by the Indian Academy of Sciences, and the target which are advanced but written in a manner which is simplified and very easily understood. Okay? So this journal is freely available online. If you have access to the internet, just go to Google and type Resonance Indian Academy of Sciences and look for the loosely bound relation. There is a very nice article which you can read. Very accessible. Something made easy.
I didn't.
Can you tell me more research area aspect for non-material fluid? Law of behavior.
More research area for non-material.
Research opportunities in non-material.
So you mean in terms of opportunities or research areas? Or applications?
Research area. What we do?
Okay. I have added up already polymer and all this. Do you want to add a few more?
So, you would have seen in the presentation on various things, for example, polymeric fluids, suspensions. I had mentioned foams. Professor Ratul mentioned amorphous materials. So, what we study as non-Newtonian fluids as undergraduates and master students, when we further look into it, we essentially are trying to understand the origin of, say, the non-Newtonian behavior. So say if you're looking at cornstarch, you might have seen a couple of YouTube videos on how cornstarch is a shear thickening material. So of recent, some research has revealed why cornstarch behaves in such a strong shear thickening fashion. So in terms of research areas, that sort of, it doesn't summarize it, but if you, it at least gives you a picture of what kind of work might be involved. Now in terms of industrial applications, there are, they're just huge. Anything from, say, petroleum drilling to drilling for petroleum oil, or to, for example, most of the things in this room would, manufacturing them would have involved some handling of some non-Newtonian fluid, right? So some say, I know that the plastic bottles that we have, they are made using the polymeric material by sort of, setting it in a cast. So handling that polymeric material during the extrusion time is important. So essentially the applications are huge. Most of the materials you use day in and day out, toothpaste, shampoos, soaps I mentioned, they are all non-Newtonian materials. But there's no such single formula you can use to study non-Newtonian material. Each material has its, its unique peculiarities, and we sort of study them appropriately. Sorry?
Is it difficult non-Newtonian fluid?
Yeah, just to add up a couple of points, what Professor Jyoti told. Actually, in a single sentence, what we are trying to understand is that structure and property relation. Okay, so we hardly do Newtonian fluid. We are mostly doing research on non-Newtonian fluid, if you carefully look at the presentation, because sometimes it is complex flows, and the outcome of that is not simple like a non-Newtonian. But we are trying to understand what should be the constitutive relations. If you know that, half of your job is done. Sometimes in a Newtonian liquid, if you put some viscoelastic solutions, the whole behavior changes, okay? Because the structure changes. So the overall objective is to find out structure and property correlation in from different angle. Okay? That is probably what we are doing.
So what is the difference between nanofibers and nanoparticles?
height, the difference is only in the length scale. Nanofiber, this L by D dimension will give you the same concepts. For a fiber and a particle, you can apply the same concepts. I am not a nano expert, by the way. Can you add a few points? I think the difference is only length scale ratios, aspect ratios. Yeah. But yes, I can tell you one thing. Synthesizing a nanofiber is much difficult than synthesizing a nanoparticle. Okay, provided if you want with a perfect dimensional nanofiber. So that's why the procedure changes. I have put on slides on that how overall nanofibers synthesized by electrospinning and all those things. This much only I know, but if you want to know a little more, I think you can talk to Professor Venkat Gundwala, who is working in this area.
So, in the numerical approach, distinct element method.
Discrete element method.
Yeah. Is it related with the particle velocity distribution, or what we will find out?
Yes. The thing is that suppose two particles collides, then there will be exchange of momentum. Okay? Two particles, when they will collide, there will be exchange of momentum between two particles. So they will return back with some velocities. Now to calculate the velocities, you may use hard sphere collision, as if there is two particles are hard sphere, there is no overlap. When they will come within the diameter, they will go bounce back. Okay. Now you can put some elastic or inelastic behavior, as if there is no loss of energy or there is loss of energy. This is a very simple thing. These are called hard sphere collision. Okay. Now in discrete element model, what we do, we allow little overlap between the particles. Okay. And we apply spring and dashpot model, which takes care of, spring will takes care that they are bouncing back, and dashpot will take care how much energy dissipates during the collision. Okay. So almost similar these, but the thing is that objective is to find out velocities. Okay, after the collision.
For that we need some simulation. This
Yes.
is the model.
This is model. Yeah. So you have to track all the particles, their approaching velocities, and you apply your discrete element model to get the output velocities, means the bounce back velocities.
What is any software you use? Simulation.
I do not use software, but there are softwares like lamps and lights and all these things. This part I do not use. But one of my master student used a part of lamps package, Okay. Can you repeat the question also?
So the firefighters, the pumps which they use, the water flowing out is very turbulent in nature. So what if we replace that with a laminar flow? Which one would be more effective, the turbulent one or the laminar one?
Yes. To answer your question, we have to think a bit. When you are making the flow turbulent, then you have to supply some more energy. Okay, by a pump or a motor, whatever be the thing. There will be some loss of energy. At the cost, in a turbulent flow, you will get higher transport coefficient. Okay, what happens? How the firefighter fights with the fire? Okay, the water should evaporate faster, take the latent heat, so that it decrease the temperature of the flammable material, and it will decrease. Okay. Now, in most of the cases, what pumps sort of they are using, it can provide this much power so that your flow is a turbulent jet. Okay, it is nothing but a turbulent jet. Okay. Now my own understanding is that there is nothing wrong to use turbulent, because you are wasting a little bit of energy, but these are the emergency cases. Okay, so and your coefficients will be very high in case of turbulence, so that fire, you can extinguish the fire very fast.
I mean, there's something that I just wanted to mention since we have asked that question. Firefighters traditionally have faced this problem that typically the flow rates at which they operate, the flow is turbulent, and typically in operating close to high-rise buildings where you cannot go very close to the fire, and so you would want a mechanism by which you can push water by a very long distance without wasting too much energy. Now in turbulence, it's hard to even know. I mean, there's a lot of drag and all that. So there was this thing called little bit of polymers which have been added, and it has been known for quite some time now that if you add a little bit of polymers in that water, which does nothing much dramatic to the properties of that water, it can, so it dramatically reduces the drag, and so for the same power input you can push water by a much higher distance. So this is something which firefighters already use.
They have added a polymer
A little bit of,
flow from turbulence to laminar.
So whether the flow is laminar or turbulent depends on the rate at which you are pushing it and the properties of the fluid. Okay, so you have only control over the Reynolds number. Okay, so as long as the Reynolds number is above a certain number, you are very likely to get a turbulent flow, and then you do not have control over that. But what you would ideally like to do is pump water over longer and longer distances without having to burn too much fuel in your pump. Okay, so that's what these firefighters do by adding a little bit of polymer. Maybe he has already spoken.
In my slide, those slides are drag reduction. So it is called turbulent drag reduction. Little bit of polymer you will add, they will align the undersphere, and that polymers will help to reduce the drag. So that with the same power, you can put much more, but it is in turbulent. But the drag which is expected from that, is not there. You can change the material turbulent drag